Okay, in the last movie clip, we have derived the excess carrier concentration. That is, excess hole concentration in the N side. I mean, if you imagine the cross-sectional view of PN diode, once hole is dived into the N side region up beyond the depletion layer, how the hole has been diffused out. So to explain the diffusion mechanism mathematically, we should get the excess carrier concentration as a function of X as well as applied voltages. So we have completed and built up the full equation for this. Okay, so it turned out that there is a P and naught that is actually, Ni square over N sub D, and the applied voltage and diffusion length of holes, which is the minority carrier in the N side. So from this fact, in PN diode, the major driving force for building up the current comes from the minority carrier instead of majority carrier. Okay, so in that sense, PN junction diode is said and classified as minority carrier device. And similarly, we have derived fully the excess electron concentration in the p side as a function of x, right? But you know the meaning of x prime and x2 prime. And once you know the at thermal equilibrium in the p side electron concentration and how much voltage you have applied and what is the diffusion length of electrons in the p side, okay, so minority carriers diffusion length, then you can build up the excess electron concentration in the p side. So these two equations are the final goals for step number 1 in ideal diode analysis. Okay, so we have got the full equation for those two terms. Okay, all right, so we all done and we all set for step number 1. Next one is step number 2. As I have briefly introduced, what we are going to do in the step number 2 is simply plug in the full equation into this equation. What does this equation for? Yes, the diffusion current density equation. So this is electron diffusion current density can be written as unit charge times diffusivity times doping concentration gradient. Okay, so physically speaking, this is a cross-section of your p-n junction diode. So once electron has been injected into the p side, and those electrons would go throughout the quasi-neutral region of p side by diffusion mechanism. So if I draw the x2 prime scale, and that is delta np x2 prime, then so np naught times exponential qva over kt minus 1. That is the initial value of excess carrier concentration, and it is going to be decreased exponentially. And in the end, the excess carrier concentration is approaching to 0. Okay, that means the injected electrons would be annihilated with holes in the p side. Okay, so by solving this equation, we're gonna determine the minority carrier current density, actually diffusion current density. Why diffusion current density only in the quasi-neutral region again? Yeah, you remember this question. You can answer this question. Uh, Once a certain bias has been applied across the PN diode, this applied voltage should be almost 100%, 99.999% of VA should be dropped across depletion layer. So I said the junction voltage drop is almost identical to the applied voltage, so that in the quasi-neutral region in the P side and N side, no voltage drop. That means no electric field. No electric means no drift current available. Okay, cannot be formed in the quasi-neutral region. Basically, it is reasonable, but technically speaking, it is not true 100%. Definitely, there is a tiny amount of voltage drop across quasi-neutral region, but we are going to ignore that small amount of voltage drop in the quasi-neutral region in the ideal diode analysis. That means in practical diode or in non-ideal diode, the voltage drop across quasi-neutral region should be taken into account in determining the final value of diode current. Okay, all right, so in this movie clip, let's solve and let's tackle down the step number 2. Okay, let's go on. All right, there we go. So this slide is the very first slide for step number 2. So in PN diode, in the P side, again, think about the cross-sectional view of PN junction diode, PN. Now electron has been injected into the P side and how they are diffused within the P side quasi-neutral region. So electron concentration, no. Electron current density caused by diffusion mechanism is defined by this equation. So just plug in the full equation that we have obtained from step number 1. So what was it? Delta NP extra prime. What was it? Yes, NP naught times exponential QVA over KT minus 1 times what? Exponential minus x2 prime over L sub n. So just plug in here and take a first derivative with respect to x2 prime. So NP naught is constant and exponential QVA over KT minus 1, which is another constant from the perspective of x prime, x2 prime. And the only thing that you should take into account in taking the first derivative to x2 prime is this term, right? So minus and 1 over L sub n, okay? So minus 1 over L sub n should be multiplied with a minus qdn. So minus qdn, that is simply the constant. And once if you take a first derivative of delta np extra prime minus 1 over ln times and np naught exponential QVA over KT minus 1 times exponential minus x2 prime over ln. And now those two minus are cancelled out to each other and QDN divided by ln. So you can see that term here in, and MP naught is here, and exponential blah blah minus 1 is here, and the last term exponential minus x2 prime over ln is here. Okay, so we're all done. So step number 2 is very simple. So in the P side, we can write down the electron diffusion current density denoted as J sub n as this. Okay. Similarly, we can repeat the same work for the N side again. So N side means a hole has been injected into the N side and they're going to be diffused out across the quasi-neutral region of N side. So hole diffusion current density is defined as with this equation. So now you know the full equation for delta P and x prime. What was it? Yes, P and naught times exponential QVA over KT minus 1 times exponential minus x prime divided by L sub P. So plug in this value into this term and take a first derivative with respect to x prime. So P and naught is constant and exponential blah blah minus 1 is also another constant. And here minus divided by LP, those coefficients should be moved out. So minus Q times dP times here minus 1 over LP, and the constant Pn naught, another constant exponential QVA over KT minus 1, and the minus X prime over LP. Okay, so this minus minus are cancelled out to each other, so Q dP over LP. So you can find that term here in, and Pn naught and exponential QVA over KT over minus 1 here, and you can find the last exponential term. Okay, we all set. In the step number 2, we have obtained electron diffusion current density and hole diffusion current density. So by simply summing up those two terms, we can build up the total current density across the PN diode. What was it? Again, in PN diode, for a given externally applied bias, a single value of current should be flowing across PN diode. So the total current density should be defined as I over divided by A. A means cross-sectional area A. And this current should be same wherever the X position is, right? So you can simply sum them up, two components, electron current density and hole current density, but at the same position. Suppose that at the edge of the depletion layer in the N side. But in doing ideal diode analysis, one of the assumptions was no recombination and generation in depletion layer, right? So let me switch the color of my pen. So the electron concentration at X of Xn should be, no, all the electrons, they are existing near the edge of the depletion layer, I mean at X of Xn here, should be injected into the P side. So what would be happened in the middle of the depletion layer? These electrons, while it is going toward P side, what kind of mechanisms would block the movement of electron in the middle of the depletion layer? Well, definitely in the depletion layer there is built-in electric field from N to P side. So electron would take an experience to be pulled back because of the electrostatic force coming from the built-in electric field. However, the diffusion force is still strong, even much stronger than the drift force. So that's the reason why electrons can be injected into the P side for a given forward bias. Anyhow, my question is, what would be happened in the middle of depletion layer while the electron is being injected into the P side? Yes, recombination and generation. No other mechanisms available. So if once a single electron has been injected into the depletion layer and another hole has been injected into the depletion layer, if they are recombined to each other, then we're gonna lose that electron and that hole. But in ideal diode analysis, we have assumed that there is no recombination generation happened in the depletion layer. So J sub n at X of minus XP should be identical to the Jn at X of plus Xn, because I have moved from Xn to minus XP. I mean from the edge of the depletion layer in the P side to the depletion layer edge on the P side. So while the electron is moving from this edge to that edge, I mean the xn to minus xp, what would be happened? No, nothing happened. So current density, electron current density would not be affected at all. So we can conclude that Jn at x of xn is perfectly identical, perfectly the same as the electron current density at x of minus xp. Okay, so from the first term can be rewritten as Jn at x of minus xp. Plus, the second term, you can simply write down the second term as it is. X is plus xn. Okay, so now you can see this equation. And now let's switch the coordinate system from x to the new coordinate system on each side. Now we are in the p side, so we are going to use the x2 prime new coordinate system. Again, the new coordinate system is this. To refresh your memory, that is x of 0 and that is plus x. Okay, but in n side, the depletion h x of xn is newly defined as the new origin point of x prime x prime coordinate system. Okay, that is x prime is positive. And on the p side, the edge of the depletion layer is defined as x2 prime of 0, and this direction is defined as positive regime. Okay, so now I'm talking about the electron current density. That means electron has been injected and then it is going to diffuse the out. So we're talking about the p side uh, current component. So let's switch it from x to x2 prime. So x is minus xp is this point, right? Minus xp, this point. That point is corresponding to the x prime of 0. So there we go. And similarly, the x of xn is corresponding to the right hand side depletion layer edge that is corresponding to the x prime of 0. So there we go. Okay, so now I guess let me erase my note. So now going back to the equation, the first one shown in this lecture note, when x prime 2 prime is 0. So plug in 0 value into the x2 prime here. Then exponential to the 0, which means 1, right? So this component can be written as q dn ln and p naught times exponential qva over kt minus 1. Okay, what about this? Yes, go to the second line here. Jp when x prime is 0. So plug in 0 value into here, then the last term value is 1. So the second term here in is q dp lp p and naught exponential qva over kt minus 1. Okay, now it's time to sum those two terms. What is the common term? Yeah, q and this exponential blah 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 here and another q. Okay, so q is here and exponential blah 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 is here. There we go. What else to be left behind? Yeah, this guy and that guy. Okay, so let me write down it. Q total j is q and exponential qva over kt minus 1 and dn ln and p naught plus dp lp pn naught. And now np naught was what? Yes, ni squared divided by na, and pn naught was ni squared divided by nd. If you missed this point, let's move back. There we go. np naught is ni squared over na, right? And pn naught is ni squared over nd. So remember those, and let's move forward. Yeah, there we go. And P naught is Ni square over Na. P n naught is Ni square over L Nd. So now Q, Ni square is common, so let's take it out. So Q times Ni square and exponential QVA over KT minus 1, and the left one is dmln and Na plus dp lp and d. Okay, so now we got the diode equation, this. Okay, so instead of J, if I would like to, if you would like to use a current I, simply take into account the cross-sectional area of PN diode. Okay, so here in, let me erase my note. Yeah, so take a look at this term. Q, Ni, D, L, Na stuff. These guys are nothing to do with VA. I mean, whatever the externally applied voltage is, Q, Ni, Dn, Ln, Dp, Lp, Na, Nd are not affected at all. They are kind of constant. They are the parameters of PN junction diode, device design parameters for your PN junction diode. Okay, and they are kind of constant. So now let me write down it as J sub naught and exponential QVA over KT minus 1. And instead of current density, let's use a current. So it's J, usually JS. So IS over A. Then just cancel out the cross-section area, then you're gonna get this equation. I is equal to IS times exponential VA over now KT over Q minus 1. And usually this KT over Q is defined as a small V sub Vt, thermal voltage. As you know, at 300 Kelvin, what was the value of the thermal voltage? Yes, 26 millivolt. Okay, so in the next slide here, I is equal to IS or I naught. Both are okay, I naught or IS, depending on the textbook and paper, research paper, they prefer to use IS or I naught. And this I naught or IS is defined as, cross-sectional area, Q, Ni square, dp, blah, 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 blah. All right, so think about the doping concentration, Nd and Na. My question is, in the PN junction diode, in the P side, there is donor and acceptor. In the N side, there is donor and acceptor. Which Nd, this or that? Which Nd should be included here? Are you confused too much? Then go back to the first slide in the ideal diode analysis again. There we go. In the P side, NP naught was Ni square over Na. This Na that I have used. Na means in the PN diode, the P side, majority carrier in the P side. Okay. Similarly, the Nd comes from the N side. So how much donors are necessary to make N-type material in the PN diode? Okay. So here in the diode equation, Nd Na means this Nd in the N side, and Na comes from the P side. Okay, so you should ignore the acceptor concentration in N side, and you should ignore the donor concentration in the P side. It is not contributing too much to the diode equation. But more technically speaking, instead of Nd, it should be Nd minus Na. Where? Which Na? Yes, this Na. So basically, this Nd means net dopant concentration, I have to say. So N side Nd, but actually Nd minus Na. but usually this Na is much smaller than a donor concentration in the N side. That is the main reason I have simply used the Nd. But more specifically, this term should be Nd minus Na in the N side. And instead of Na, more technically speaking, that should be Na minus Nd in the P side. Okay. So what was dP? dP is a whole diffusion length that is defined as no. Again, dP is once if you remember the Einstein relationship, dP over mu p is constant kT over q. So once you know the mobility of a hole, so this mu p comes from P side or N side. Go back to the analysis again. Where does it come from? dN dP. Yeah, in the N side, how the hole, so minority carrier is moving, right? So minority carrier. So keep in mind that minority carrier can determine the diffusion length and diffusion constant T and L. Okay, so let me erase my note again. So here in dP LP comes from the minority carrier. So in the PN diode, once the hole is injected into the N side, this minority carrier's diffusion constant and this carrier's diffusion length. So dP LP should be obtained from the N side. Okay, so dP LP value should be obtained from the N side instead of there is a dP LP to be used in the P side because there is a hole in the P side and this hole has its own diffusion constant and diffusion length, but they are not be used in diodication. The minority carrier's diffusion constant and minority carrier's diffusion length should be included in the diodication. Okay, so similarly, this Dn and Ln comes from the electrons in the P side. Okay, so these electrons in the P side has its own diffusion constant and diffusion length. Okay, so this Dn, Ln should be included in the diodication. Okay, so previously I have made this kind of question. So for a given PN diode, there is dP, dN, LP, Ln. There is another dP, dN, LP, Ln, right? Because there is a hole and electron. Here, hole and electron available in P side. Definitely more holes included in P side and more electrons in the N side. But each carrier has its own, its own diffusion constant and diffusion length. Each hole has its own diffusion constant and diffusion length. But when you're calculating this I naught or IS, what kind of value should be used in this diode? Okay, so I'm going to give you 8 different device parameters. Which one should be used to estimate I naught? Okay, that would be challenging without uh, any try on your side. Which diffusion constant, which diffusion length should be used in building up the saturation current or I naught? That would 100% confuse you a lot and a lot. Okay, so think about this issue. Okay, and one more note is I naught or IS is defined denoted as a saturation current. So you will see that why saturation current. The reason why I naught or IS is named as saturation current in the near future. So just take a moment to figure out the physical reason why saturation current is named as it is. So in this movie clip, we have built up the ideal diode current voltage characteristic. So for a given PN diode, the bias and voltage are defined as this. So what is the IV characteristics? Okay, it turned out that I naught times exponential VA divided by terminal voltage minus 1. Okay, so instead of this figure, if I'm using the circuit symbol like that. So plus minus V, and current is flowing in this direction, following the passive sign convention, as you know. Okay, for a given resistor, you know, R. So I is the function of F. What was it? Yeah, 1 over R times V. Very linear relationship. But in diode, their voltage current characteristic is very non-linear. So once diode is included in your electronic circuit, that circuit is named as non-linear circuit. But if your circuit is only built up with resistors only, then people are saying that this is a linear circuit. Okay, all right. So in this movie clip, I have explained the meaning of the full uh, analysis for ideal diode. Okay, so please read and try to, you know, derive ideal diode equations by yourself, by your own hands, without any help. Okay, just for a given white paper, write down your own equations and write down your own assumptions, and in the end, you should derive the IV characteristic of PN junction diode. Okay, so that would be your last job of in this week. So please do that, and see you in the next week. Thanks for your attention. Bye bye.